Good evening, everyone. Welcome. My name's Carl Schneider. I'm the editor of Farmers Weekly, and on behalf of Farmers Weekly and Syngenta, I want to give you a very warm welcome to tonight's lecture, the third in our Arable Horizon series of lectures. Now, the idea behind these lectures is really simple. Firstly, we identified what we thought were the 5 areas of science and technology that were going to have the biggest impact on the way we farm, or the way we grow crops over the next 20 to 30 years. And then for each of those areas, we've identified people who are leading researchers in that field to talk about how developments in that field could change the way we farm over the next 20 to 30 years. It's a simple concept, but so far it's worked really well. Now, these lectures take place in front of an invited audience, so thank you very much for coming along here. It's also streamed live over the internet, so we've got an unknown number of people watching this live over the internet. And it will be available, the video from the event will be available to view and to download immediately after this lecture on the Farmers Weekly website or on our YouTube channel. And it will be written up in Farmers Weekly in 2 weeks' time. Now, I said we've already had 2 lectures in this series. The first one was on plant breeding and genetics, and the second one was on soil science. Today, our subject is robotics and automation. I'm personally very excited about this topic as a former physicist and engineer. And it's certainly a very hot topic at the moment. I always wake up listening to Farming Today and then followed by the Today programme on Radio 4. And I woke up 2 days ago to hear them talking about robotics on farm. And there was a big piece in the Financial Times on Tuesday about farm robotics, which actually featured our 2 speakers tonight. And I think the reason is clear that firstly, there have been some really exciting technical developments in this field that means that over the next few years, I think we can expect to see a stream of exciting new technologies, many of which we're going to hear about tonight. And so there's the push of new technology, particularly in some fundamental technology areas like robotic 3D vision. But also there's, of course, the pull of the shortages of labour on farm, and with the fear of those getting even worse in the post-Brexit period. It's fantastic to be here in the National Space Centre in Leicester. I've wanted to come here for years. I'm a child of the 60s, so I grew up watching the Apollo space programme, so this is a fantastic place for me. But I think it's particularly appropriate given the impact that Apollo programme had on a whole generation of people like me. I would hope that the exciting new technology that's coming onto our farms over the next few years could have the same impact on a new generation of people excited to come and work in what I still think is one of the most exciting industries on the planet. I want to thank Syngenta for supporting these lectures. We couldn't do this programme without Syngenta. It costs a lot of money to put these on. You can see there's lots of technology around streaming this over the internet. And I want to thank Syngenta. It shows their commitment to the technology and the future of farming, that they're willing to put money into events like this. So thank you very much, Syngenta. Before I introduce the speakers, I just want to say a couple of things about the way things work tonight. These are called interactive lectures, and there is some real interactivity here. So firstly, we have a technology called Slido. Can we put that up on the screen? So all of you, if you've got a mobile phone in your pocket, if you want to take it out now, if you haven't already done this, and go to www.sli.do, that's Slido, and it's a very simple interface, and then there's a box on it that asks you for a code, and you put in the code, that code there, 3385, and that makes sure you're on this lecture. Don't put the wrong code in, or you'll be answering questions to some completely different lecture somewhere else in the world. So if you go to Slido, put in that code, then you can take part in the discussion today. So firstly, we're going to be asking some polls. I'll give you an example of one in a moment here, and you can give your answers to those polls. We can get a feel for the way people think, both here in the audience and people on the internet can vote in these polls. But also, later on, I'm going to ask our 2 speakers to join me on the stage, and we're going to have a Q&A session. And at any point during the evening, if you want to type in your questions into Slido, then we'll be drawing our questions later on from the questions that you ask. So at any point during the evening, if anything that someone says prompts a question in your mind, just type in the question on Slido, and it'll be fed through to us in that Q&A session later on. Now, the second piece of interactivity is something called a microphone ball. Has anyone come across a microphone ball before? Can someone throw me one? Actually, it's probably going to be dangerous if you throw it from there. looks like a giant M&M, but this is a microphone ball. So when we ask the questions from the Q&A, I'm going to ask you to put your questions on Slido. If you're really nervous, you can do it anonymously, but I'd ask you to put your name on the question and indicate whether you're in the room rather than on the internet. And if you're in the room, I'll get you to ask the question yourself rather than me just read it out on the stage. And when I call you, I'll throw you this. So Adam, can you demonstrate? I'll throw it at you like that, and you'll catch it just like Adam did then.
Hello, hello.
You can see the microphone works in the ball, then you can throw it back to me. So it avoids that sort of embarrassing kerfuffle when microphones get passed around the audience. And the last thing about the interactivity is, like all things these days, there'll be a discussion on Twitter, and the Twitter hashtag is Arable Horizons, all one word. Okay, on to the big event tonight. We're very lucky to have two fantastic speakers tonight. I'm going to introduce them one at a time. They're going to speak one after the other. And our first speaker is Professor Tom Druckett. Tom is Professor of Computer Science at the University of Lincoln here in the UK, just down the road, where he leads the Lincoln Centre for Autonomous Systems. Now, the area he's researching into includes autonomous robots, artificial intelligence, and machine perception, with applications including agriculture and assistive technologies. Now, Tom's going to look at the broad field of on-farm robotics and automation and try and paint a picture of where that could be taking us over the next 20 or 30 years. So I'll ask Tom to come up now, and then I'll introduce our second speaker in a moment. So could you put your hands together for Professor Tom Druckett?
Thank you very much to Carl and the team for inviting us to speak today, to speak about agricultural robotics, or perhaps I should say terraforming, given that we're in the National Space Centre here in Leicester. Yeah, that's about as good as it gets, I'm afraid, but I'll do my best. So yeah, my name's Tom Druckett. I'm Professor of Computer Science at the University of Lincoln. I lead our robotics research group, which is called the Lincoln Centre for Autonomous Systems. We've been going for about 10 years now. And in the last couple of years, we've got together with colleagues at the University of Lincoln to form the new Lincoln Institute for Agri-Food Technology, which is led by my colleague Simon. So that's a new institute that brings together research from across the University of Lincoln: computer science, engineering, life sciences, food manufacturing, agriculture. Simon, tell me if I missed anybody out. To basically tackle really challenging real-world problems in agriculture. So basically, I speak robot, and Simon speaks farming. So if we need a translator, then Simon's the man to go to. Okay, so just to give you a very little bit brief background on our research group, we're basically about 30-odd people at present. We're 9 academic staff, and we're about to recruit for two more lecturers. So if you know anybody who might be interested in a job, please let me know. We've got about 25 postgraduate researchers as well, and we're currently recruiting for a number of new projects, so we expect that to increase. What do? We work on enabling technologies for robotic systems. So we're big into perception, especially vision systems, so making machines use sensors to make sense of the world around them, and I'll talk quite a bit about that today. We're big into learning, and I think that machine learning especially, this is an important topic for agriculture especially, and we'll hopefully convince you why. We also develop technologies to enable our systems to make decisions. So for example, to decide whether a broccoli plant is ready to harvest, or whether a particular plant is a weed and should be exterminated. We also do research on developing control algorithms, so that's to actually make a robotic actuator motors do the thing that we want it to do. And we also develop technologies for interaction, meaning interaction with humans. And I think that would be a good point actually to go to my demonstration, please. So, okay, it actually worked, which is good news. So, basically you can see a display here, and it's reflecting the output of this particular camera here. If I pick this camera up and move it around, you can see some green blocks on the screen, which are heads of people that have been detected. It's mainly detecting people here in the front row. Okay. So this is basically a 3D camera. Does anybody recognise it and know where it came from? Yeah? It's from a Microsoft Xbox. So it's actually an interfacing tool for a Microsoft Xbox gaming system. So it came along in 2010. And the basic idea is that instead of using a joystick or a handheld controller, you use your own body as the controller. So you stand in front of the sensor and you make gestures, and then it recognizes those and uses them to control your character in the game. But since 2010, this sensor's also been hacked and adopted by the robotics community, and it's really revolutionized robotics research. Why is that? Well, why it's different from a conventional camera, like a color camera in your mobile phone. A conventional camera, color camera, will have 3 channels of information. It'll give you red, green, and blue information. This kind of sensor also has an additional channel which gives you depth information. So basically, as well as giving you color coordinates, it gives you the geometric coordinates of things in the world. So, and that actually turns out to be really powerful, as it allows us to make much more robust algorithms for sensing than before, when we had to rely just on 2D vision. So if I can just show you what's on the screen, there's a color image there, so you can see yourselves there. That's the depth image, and what we have over here is something called a point cloud, and that's basically a bunch of points in 3D space, and they're also colored with the data from the color camera. And in fact, if I would grab the mouse, just to convince you this is actually 3D, I can rotate the thing around, and hopefully you'll see that that's not just a flat 2D image, that's a bunch of 3D points. So what we're running here is a piece of software which was developed together with colleagues, by my colleagues at the University of Lincoln, together with colleagues on a collaborative research project which is called Strands, which is aiming to build long-running robots. It's a people detection system, and it was actually deployed recently on a mobile robot in a care home in Austria, and we just reached a milestone that the robot was able to run for 100 days fully autonomously in a care home, performing certain tasks to assist the people there. And it was relying on this technology to detect and recognize the people around it, and then to be able to use that to perform in a hopefully intelligent way around people. Just briefly, without getting into too many details, how the algorithm works. It basically needs to work out where the floor is, so it needs to estimate roughly where the floor is, and then it's basically looking for tall, roughly human-sized objects, and it's basically an upper body detector. So it's looking for a round thing that looks like a head on top of a blob that looks like a torso. You can fool it actually. If you would get a big box and put a balloon on top, you could probably fool it into thinking there's a person there. So why do I think this is important for agricultural robotics? Well, robots and humans are good at different things. So I don't think we'll go to fully autonomous robots for any time soon. I think that there's a space for robots and humans to work together, to collaborate together. And I think therefore for the robots to be useful working companions, they need to be able to recognize the people around them and perform intelligently together with the people. So yeah, if I could go back to the presentation, please. So that's the technologies we're working on. We're working in a number of different domains, including agriculture, which I'll talk about tonight, but some other related areas as well. We're working in intralogistics, which means warehousing, so making smart mobile systems that can move around in warehouses, for example, food warehouses. We're also working on transportation, autonomous driving systems, for example, which could be applied in agriculture. Security might be another one as well, because if you, as a farmer, are going to invest lots of money in an expensive robot for your farm, then it might be nice if the robot could also have other functions as well. For example, being a security guard that could keep a watch on valuable equipment, or look after the welfare of the people and the livestock on the farm. So that's a brief overview of what we do. So here's a list of current projects. We have a number of other projects and new ones starting, but these are the official ones that we're currently getting funded by the taxpayer to do. And I'm going to talk about some of these projects in detail in the rest of this talk. So one project, we're doing high resolution soil moisture mapping, and we've got a brand new sensor called the Cosmos sensor, which is actually inspired by Mars rovers. Simon told me to say that, so yeah, so which is quite appropriate for the National Centre for National Space Centre. So we're also interested in other properties of soil quality. So, for example, microbial activity, compaction, and so on. So, working together with colleagues at the institute. So, as you've seen, we're using a lot of sensing technologies, 3D imaging technologies. So, we have a project on using that 3D vision to do robotic weeding, which I'll talk about a bit later on. We've also got a project on robotic harvesting broccoli. So it turns out actually sensing a broccoli plant is not so different from sensing a human. It's basically a round thing on a stick, if you like, above the ground. So actually the algorithms that we develop for detecting broccoli are not so different from the algorithms for detecting people. So we're also doing a lot of work on harvesting, bio-inspired vision systems, and we've also got some new projects starting in manipulation, robot hands for picking fruit and even mushrooms, I believe. So we have a brand new project as well, which we'll talk about shortly, where we're developing robots for berry production in polytunnels. And we're also getting into intralogistics as well, especially for the food industry. So that's sort of a brief background and overview of the projects that we're working on at the moment. So let's look at how this technology might develop and where it can go. So one of the sort of underlying questions that's fundamental to this research is, can we make our agriculture more efficient and sustainable? So we're faced with a growing worldwide population. We basically need to do more, grow more food and other crops as well, biofuels and so on, with existing resources, and we need to feed a growing population. So how do we do that? How can we scale up the agricultural systems that we have now to produce more with the current resources? Well, to try and look to the future, it's good to look to the past. So sort of if you look at the development of agricultural machinery, started off in antiquity with the invention of the plough, and that was pretty much the state of the art for hundreds of years until the Industrial Revolution, and then came along steam power, and then we got to tractors. And the trend in recent years has been towards bigger and bigger tractors. This is the way to scale up the technology, to build bigger and bigger machines. But there are a number of issues with this. So soil compaction is one. Using the reliance on fossil fuels is another. So is this really a sustainable long-term solution? Well, together with a number of colleagues that I see sitting in this room, we think there is an alternative, and that's to build autonomous robots. So rather than scaling up by building bigger and bigger machines, you could have a fleet of more and more smaller robotic systems which could function off electric power, which could potentially do the job even more efficiently. So just to mention how is this going to come about, the technologies I'm going to talk about today require platforms to run on. So probably the closest route to market would be to basically retrofit existing farm vehicles. So colleagues at Harper Adams University have been very successful and are very good at retrofitting, at roboticizing farming vehicles. And this is an example. It's one of your slides, Richard. I'm not sure from a recent presentation of an autonomous tractor. So I think in the short term, the robotic technologies that I'm talking about tonight will be deployed primarily on existing farm vehicles, tractors, sprayers, or whatever. In the longer term, I think we can also see something like this. This is a lightweight, electric-powered mobile robotic system. It's one that we're working with now at the University of Lincoln, and it was actually developed by our colleagues at the Norwegian University of Life Sciences. So this is work done by Professor Paul From, who's now a part-time professor at the University of Lincoln, as well as a professor in Norway. And I'll just show you a couple of videos of our robotics platform, which is called Thorvald, just so you can see it working. So basically, this is a mobile robot. It has a battery life of around 12 hours at the moment, but that of course depends on the payload and the operations that you're trying to perform. So it has 4 independently powered wheels, and there you can see the robot in the field. Is that broccoli? It looks like broccoli to me. So there you can see, get an idea of the mobility of the platform, and there's actually a similar sensor to this one mounted on the front to do some measurements there. Let's go to the next slide. It's quite a good. This is quite a good indicator of how the system will deal with very muddy conditions. So this is a field somewhere in Lincolnshire. So the system's quite manoeuvrable and is able to cope with quite severe levels of mud. In fact, I've got another video which is from Paul in Norway. This one was filmed recently in Norway, and there's a robot doing some kind of tillage operations. And you'll notice the conditions there are rather wet. So in Norway, they apparently have a 2-month growing season, and it rains nearly every day. So it's not like Lincolnshire where it's sunny every day. It's, yeah. So, and Paul's got some nice videos actually of tractors trying to perform the same task and tractors getting stuck in the heavy mud and wheel spinning and so on. So there could really be some advantages to having a lightweight platform such as this that you could use for performing robotic operations on a farm. And then finally, just to illustrate the payload, so we're told that our robot can carry a payload of 200 kilograms. So I'm not sure exactly what the payload is here, but we got two of our colleagues to sit on the robot, and just to show you that it's quite it's quite a robust and reliable system as well. Okay, so well that's our robot Thorvald. Try to remember what's coming next. So Thorvald is a nice piece of hardware. It's got great electronics. It's also got some onboard controls, fairly low-level control, for example, for controlling the 4 wheels together. But all of the demonstrations you've just seen were done at the high-level control was done by a human with a joystick. So basically, someone was standing there driving the robot by hand. So if we want to make the robots autonomous, then we need software. So if you like, hardware and software are the two sides of the coin in robotics. So you need mechanical and electrical engineering to build the hardware platforms, but then you need computer scientists to do the coding and try to develop the software to make the systems autonomous. So that's where I think robotics can add something to the agricultural world. So basically, all robotic systems or autonomous robot systems operate on a sense, think, act cycle. So they have sensors like the one I showed you here to interpret, make sense of the world. Then they have to do some kind of thinking, reasoning. So it might be decision making. It might be some planning. So working out the sequence of actions that you need to take, for example, to remove a weed or to reach a certain point in space. And then they need actuators, that's motors and implements, to actually carry out the motor commands. So the industry is already very good at building actuators. Implements for farming, for example. I think what computer science and autonomous robotics can bring to the party is the sensing and the thinking side. So in the past few years, we've had tremendous advances in both of these areas. We've got excellent now perception systems, vision systems for robots. We've got excellent reasoning systems that can work really fast, real time. And the challenge now is to put these things together and see if we can apply them to do useful things, for example, in agriculture. So these systems will need artificial intelligence. They will need vision systems. They will also need machine learning. So the reason for that is because it's impossible for us to anticipate all of the tasks and the things that a mobile robot in the field will actually need to do. We can program the robot initially, but then we know that under the real world conditions, there are always changes in the environment. There are different lighting conditions, there are different soil conditions, there are different types of crops which are changing, there are new diseases coming along and so on. So we're really, to make robust systems that work in real world environments, they need to be able to learn. So we take algorithms inspiration from the field of machine learning, and I'll talk more about this. What these systems will also need to do is to be capable of lifelong learning, to be able to adapt their knowledge over time. So in robotics now, we've got quite successful at building short-lived robotic systems that can act for a few hours. But now the challenge is to make those systems run for really long periods of time and to be able to learn and adapt and benefit from their experience. If you had a robotic system that makes a mistake, well, that's okay, but if a robotic system would make the same mistake over and over again without learning from it, then you probably wouldn't think it was that intelligent. So we need robots that learn from their experience. But as I said earlier, I don't think we're going to be looking at fully autonomous systems anytime soon. I think for the next generation of farming robots, there will usually be a human in the loop somewhere. So if you've heard of, maybe you've heard one of the buzzwords going around at the moment is Industry 4.0. Or Farming 4.0, which is supposedly the fourth industrial revolution. And there they talk about cyber-physical systems, which basically means systems that contain a human element and a robotic element. So I think this is the future agricultural robots. I think will involve robots, but also a human in the loop somewhere. So just to give, I was told you shouldn't ever put equations in a presentation like this, but, well, sorry. So one of the useful concepts is Fanout, which means how many robots can a human control. So basically, there are a couple of factors that can influence this. So one is the activity time, the amount of time that a robot can run without assistance. So if you can increase that, then you increase the fan-out, the number of robots that a person can control. But then the more time you have to interact with the robot, that means that the fewer robots that you can deal with. So actually, if you look at some of the currently remote-controlled systems, like drones in military applications, they actually have a very low fan-out. They need more people than robots. But I think in the future, you're going to see robots with a much higher fan-out, so one person can potentially control many robots. And we need this, of course, to scale these systems, to work on a higher volume. So hopefully I'll give some examples and motivate how we can possibly do this in robotics for farming. Okay, so I'm going to talk now about, to illustrate some of this stuff, I'm going to give some case studies, and I'm going to talk about some of the projects that we've had, that we've worked on in the past few years. So the first one I'm going to talk about today is robotic harvesting of broccoli. Okay. So broccoli is an interesting crop because it's harvested selectively. So some crops, they do slaughter harvesting, where you basically make a binary decision. You either harvest the whole field or you don't. But selective harvesting, you might make several passes through the field, and you only harvest the crop when it's ready, when it reaches a certain specification. And broccoli is one of the crops that's harvested selectively by hand at the moment. And typically you'll have a gang of workers in a field. There's a picture there. And they might make 3 or 4 passes through a field, looking for the broccoli plants that are ready to harvest, and then they'll harvest them by hand. So these people literally will use their left hand to hold the broccoli. The right hand has a big knife. They'll check the specification of the broccoli. Basically, this is determined by the supermarkets. Is the head within a certain size range, a minimum and a maximum diameter? Then they'll cut the crop, and then put the cut broccoli head onto a conveyor, and it will go into the back of the tractor there. So currently you typically have one person driving the tractor, and then a gang of 6 labourers who will be doing actually very skilled work because it involves an incredible binocular vision system, an incredible manipulator, which is the human eyes and hand. So here you can see an example of a couple of broccoli that are ready to harvest, one that's too big because it's gone to flower, and one that's too small. So the things we're interested in detecting with our vision system, we want to detect the broccoli, we want to be able to detect the location and the size. So we need the size to make the decision, is it ready to harvest, and the location to ultimately control a robot to cut the thing. So can we automate this? So I'm presenting here some experiments that we did where we basically put a similar sensor to this one on a tractor. So we built a kind of enclosure there. It's a box with some material that prevents too much infrared radiation from the sun getting in. There's some lighting inside. And basically you can see in the picture on the right, this is a field in Lincolnshire somewhere with the apparatus on the front, and we recorded data from the crop at various stages of the growth. So broccoli is interesting for us because, not least because it has different growing seasons in different countries. So in the UK, broccoli is a summer crop, but in Spain, it's a winter crop. So of course, as researchers working on this, we had to do a field study and go to Murcia in Spain to do some experiments and collect some data there as well. So actually for the trip to Spain, we basically we changed the setup a bit. We actually put the light box on the back of the tractor so we could mount it with a standard 3-point linkage, but basically otherwise the procedure was the same. We collected sensor data with this system, so we could then develop our algorithms and work with the 3D sensor data recorded in the field. So basically, this is an overview of the system. I'm not going to go into too many technical details, but you can see on the left that some examples of the point clouds recorded with this kind of sensor. So this is the 3D coloured point cloud data showing a couple of examples of broccoli. And on the right, there's a system architecture. Could we go to my video on this, please? Lovely. So in a moment, I'm going to start this video. Not yet. Can we just pause it, please? Yeah. So this is basically gives you an overview of this system, and I'll just run through the steps briefly. So here again, you can see the tractor in the field. So first of all, we've got a sensing step, and there you can see an example on the top left of one of the point cloud images, the coloured 3D images from the camera. And then basically we go through a number of steps. This is the image processing pipeline. This is how we process the data and how we end up being able to locate the broccoli plant. So, okay, we do some filtering on the data, we remove some noise and things. And we also have a depth filter, which basically, it's very similar to the people tracking system. We basically need to identify where the ground is. So we use a depth filter for that. Anything below a certain depth we assume is the ground, and we remove it. And then what we do with the points that are left is we group them together or cluster them, so we get some blobs of stuff, if you like. So the second image here, you can see the ground's been removed, and we've also, so we're left with a number of blobs of stuff, or objects, if you like. We've removed the smaller ones, which are too small to be a broccoli. And then, so we're left with these kind of blobs, and we have to make a decision, is it a broccoli head or is it not a broccoli head? This video is on YouTube, by the way, and it's on our YouTube channel, so you can find it there as well. So what we do, we have to get some kind of measurements from each of these blobs, which we can use to make a decision. So we look at things like the size and the shape. We extract some so-called features or descriptors that then allow us to characterize these blobs and then make a decision on whether it's a broccoli or not. So the penultimate state is classification or decision making. So we actually have to train a classifier which makes a binary decision. Is it a broccoli or is it not? And so here you can see the outputs of this. These different blobs of stuff have been numbered, and the ones that have been classified as broccoli heads, correctly in this case, are all marked in red. And then finally what we can do then is, having detected and located the broccoli in a single frame of data, we can then track frame by frame. And that's important because that makes the system more robust, and it also allows us to precisely pinpoint the location of the broccoli, so then we'd be able to control an actuator and cut them and remove them. So if we can just start the video then, please, and you'll see the way the system works. So you can see on the top left the feed from the Kinect camera, the different steps of processing. You can see the floor removal and the classification. And here at the bottom we can see the results of the tracking algorithm. So you can see basically we're able to track the location of the objects and build a so-called map. And here you can see it makes a few mistakes. There's a double detection there, but overall it works pretty well. So basically the final output of this system is a geo-referenced, if you like, map where we know which broccoli have been detected and where they are. Okay, thank you very much. If I can just go back to the presentation then. So that's an overview of our broccoli vision system. So, and there's one of the outputs. This is for the data from Lincolnshire. So you can see the kind of, you can see the plants that have been detected. There's one that's been missed there, although it might also be a missing head that's been harvested already. Okay, and overall, I won't bore you with the details, but basically we've trained this system on the data from UK and from Spain, and a mix of the two, and then we've cross-validated, meaning we've tested the system trained on the UK data, on the Spanish data, and so on. And what we found is it actually doesn't really matter which set of training data you train on. The performance is pretty similar, whichever data set you use for training, which is good. So we know we've got a good model of what a broccoli should look like. So the differences we see are in the testing of the system, are in the overall performance on the UK and the Spanish data. So for the UK data, we're getting about 95% accuracy overall, which is pretty good. For Spain, the accuracy is lower. It's about 80-something%. And that's basically, we think that's down to the, well, the different growing conditions, a different variety. There's a lot more leaf on the broccoli crop in Spain, which is occluding or covering the broccoli and making it very hard to recognize. So our conclusion from this is that it's also variety dependent, and I think for these future systems to be deployed, we'll need to get the right varieties that as well as the right technology. You know, these things have to work together for us to be able to build a robust system. You might think, how good is 95%? And the problem is no one's actually done a study of how good humans are at doing this. So we don't actually know how well humans can do this. But I would suggest that's pretty good. And the thing is that humans tend to get bored, they tend to get ill, they tend to take holidays, whereas this is exactly the kind of repetitive tasks that robots are really good at and can keep going. And this kind of camera technology will even work in the dark. So, potentially you could have these systems running 24/7 doing broccoli harvesting at the, at the right time of year. Okay, we also, just to cut a long story short, we also measured physically the size of these heads and things, so we could see how well our algorithms were able to estimate the size of the heads, because that's really important for the decision-making step. And again, I won't bore you with the details, but we've tried a number of different methods. And bearing in mind the camera's only getting a partial view of the crop, we get some pretty good results where you can see the linear relationship between the sizes estimated by our algorithm and the actual sizes of the crops on the ground. So the next steps for this are actually to take this technology and combine it with robotic actuator technology to make a full harvesting solution. So I can just show you a couple of concept designs. This is from colleagues in our engineering school for that. So this is work in progress. We can see here, step one is an actuator to remove the leaves. Step two is another actuator to cut the crop and also remove it. That's the hard bit, actually. And then you can see a concept design for a system there where you've got a large number, well, 6 of these robots mounted on the back of a tractor. So there you're going from a system where you've currently got one person driving the tractor and 6 workers. Potentially you could, well, let's say really increase the productivity of the workers, because now you only need one person to drive the tractor. Yeah, so ultimately, of course, the tractor could be driven autonomously as well. So there you go. So that's the work we've been doing on broccoli harvesting. There's one thing I didn't tell you about that system, is the hard bit is the training. And actually, it took one person 3 days to train this system. And it was actually a sixth former, a farmer's son from Lincolnshire, who came in to do work experience. So in other industries, you do work experience, you sweep the floor, you make the coffee. In robotics, you come and do work experience in a robotics lab, you do data annotation. So Adam had to sit and look through hundreds of images, of 3D images, and point out the broccoli plants. And then all of that data was used to train the system. So if we want to make these systems really useful, then we need to simplify and make this training process easier. So one of the pieces of work we've been doing at Lincoln, it's ongoing work, is to make trainable vision systems. And that's really important that there's a human in the loop and the human's able to train the system. So you don't need a computer scientist to come to your farm to set it up with it for a new task. Ideally, the system should be trainable on the farm to work with a new crop or a new setup, whatever it is. So this is an example I'm going to show you from. It was actually a system that was designed to grade potatoes, to look for potato diseases. This is a prototype system, and there's a bigger version of it that's being tested in the industry. And with this system, we were trying to recognize different types of defects that you get in potatoes. So I've become a bit of an expert now. I know what black dot looks like and common scab and things like this. So the colleagues at Potato Council actually wanted to have a system that they could train to work with different types of blemishes, and they have new ones coming, they have new diseases coming along. They want to be able to train the system and have it work and recognize different types of diseases. And this is post-harvest, but of course if you could automate this technology, then you could potentially do this much closer to the harvesting operations. You could potentially do the grading in field. So that would mean you could even potentially increase yields, because you could make earlier decisions on how to store different parts of the crop, and you might be able to stop infectious diseases like fungal infections or whatever at an earlier stage. So for a crop like broccoli, you could even do this quality assessment before you actually make the decision to harvest. So basically, without going into details, we made a nice kind of graphical user interface where the user can basically scribble on the screen and say, this is good potato, this is disease A, this is blemish B, whatever it is you want it to learn. And then the trained system's then able to use this knowledge to make decisions and basically give you a quality assessment for any new potatoes, any other potatoes you put into the system. So here, unfortunately, this is bad interface. We've used red for good potato. We should have probably used green for good potato. But you can see that, in this case, the system's able to correctly classify the different types of blemishes on the potato. Yeah, so this is a technology that we think is really important, that you could, the reason why you need to do this with a trainable system, and how agriculture is different from other industries. If you're in the automotive industry and you're making a machine vision system to inspect car parts, it's a lot easier because they come in standardized shapes and sizes. But potatoes, whatever, they're a bit like us, they're unique individuals. And I was talking to a grower of seed potatoes in Scotland who I think has got a world record for growing 667 varieties of potatoes on the same land. You cannot make a vision system that will work for every kind of potato or any kind of crop. So, as an example, white potatoes, when they get too much sunlight, they go green, but red potatoes go black. So if you make a vision system that works for white potatoes, it won't work for red potatoes. So making a system trainable is really key to being able to adapt to the changing conditions, different varieties, new treatments, whatever. Okay, so I've talked about 2 examples of our work. I'm just going to talk briefly about a third one, and then I'll talk about briefly about some ongoing work and wrap up. I'll just check how I'm doing for time. Okay, I've got about 6 minutes left, so I better speed up a bit. So basically, this is another project just to demonstrate that we can do robot control as well. So this is an example of a sprayer, and it has really long sprayer booms which are spraying whatever treatments onto the crop. So the current systems have to try to level the sprayer booms to keep them at a certain height above the crop. If the height's too high or too low, then the process becomes inefficient, and you can get drift of chemicals or whatever into other fields. So the problem is that's a really difficult control problem because it's a great big mechanical thing that's sort of balanced on like a pendulum. So what we did to make this to do this is we put a laser scanner on the front of the cab of the sprayer. So this is actually a 2D laser scanner that's scanning a line about 10 meters in front of the vehicle. And then we're using that to kind of build a scrolling 3D model of the scene, which we're then using to plan trajectories and control the arms or the booms of the sprayer. So I won't go into too many details, but this is a 3D map that's been acquired of this was actually a field in February, I think, when there was only 5 centimeters of stubble on the ground. It's kind of color-coded by height, so the red bits are higher, the blue bits are lower, and you can see that even with this very limited amount of crop there, you can clearly see the tram lines and even the turning circle of the vehicle. So we get a very accurate 3D model of the scene, and then we're able to then use this to develop a robot controller. So we basically have a model of the system that we're trying to control. This is the kinematics, or if you like, the physics of the sprayer boom, and then we're able to do we do trajectory planning. So we look ahead and we plan how to move move the sprayer booms to avoid any bumps in the ground, or move up and down depending on the changes in the terrain or the crop. And then just an example, you can see where there's an obstacle there and the sprayer boom's tilting to avoid hitting that particular object. So I think that's my third example of a project, and that's ongoing work. So finally, I'll just mention a few other projects that we're doing at University of Lincoln right now. So we have a project on robot weeding, and this is with a company called Garford Farm Machinery, who are world-leading experts in building vision-guided hoeing systems. It's great because I can tell people I work on robot hoes, and yeah. So this is basically a camera-guided robotic system for removing weeds mechanically, so there's no spraying going on. So that's the kind of thing we're working on now. They've been doing this very successfully for 20 years, and we're now helping them to develop next generation systems that will use 3D sensing and so on. Just to mention other streams of work, we're working on this logistics. I mean, mobile robots that I work with, they're really good at one thing, and that's getting from A to B. So why not use them to carry things, move them around? So we do work on both in-field transportation and logistics as well. So just to highlight a new project that we've just started at the University of Lincoln, together with colleagues from Norwegian University of Life Sciences and Berry Gardens, a major company there. We're building an in-field transportation system for strawberry production. So we're not actually trying to do what it said in the Financial Times the other day. We're not trying to pick the crop. What we're trying to do is assist the humans that are picking the crop by carrying the boxes of strawberries. So actually, on the way that these production systems work at the moment, the humans working on the farm, the skilled pickers, are actually spending between 20 and 40% of their time carrying the boxes of picked fruit from A to B. So that's something that actually a mobile robot could do just as well, we think. So there we're trying to not replace the humans, but we're trying to work alongside the humans, so the humans spend more time picking and the robots spend their time transporting the crop. And we're going to be building, well, we've got some polytunnels going up at our research facility at the Riseham campus, and we're going to be working on that system there. And this system will be using some of the technologies that I showed you earlier, like the people tracking technology, because if you're going to work together with people in an environment with humans, you need to know where the people are and not kill them. So last but not least, we've got a new European project as well with a number of partners, which is to develop similar technologies, but for warehouses. So we've got a project with partners from Sweden and Germany and Italy to build the next generation of warehousing systems. And we're building, if you like, smart forklift trucks. So again, this will be an environment where there'll be a mixture of humans and robotic systems working together. And we'll do some of the software technology to make these forklifts aware of their surroundings, aware of what the people are doing, and able to work together with people to increase the productivity, increase the efficiency of warehousing operations. Okay, so that's the end of the sort of case studies that I wanted to present. Just to mention briefly other bits of strands of work that are ongoing and new things I didn't have time to mention. Well, we've always been interested in robot mapping. We want robots to be able to map anything, basically, know what the stuff is and where it is in the world. I think there's a general trend, especially for crops like vegetables and beets and things, to go towards per plant operations. So being able to identify and measure properties of individual plants, and then to be able to use this for applications like selective spraying, weeding, selective harvesting, some of the examples we talked about. We're also I think as well as monitoring the health and quality of the crop, there'll be increasing interest in future on monitoring the quality and the health of the soil as well. So we've got projects, for example, measuring soil moisture, as I mentioned. So that's my timer telling me that I've run out of time, so I'm gonna finish off. So we're measuring other soil properties as well, like compaction, conductivity, microbial signature. We're also working on in-field transportation logistics, and we've got some new projects starting in robotic manipulation for picking fruit. A new colleague, Professor Gerhard Neumann, who's a specialist in robotic manipulation. So finally then, this is my last slide. I'm going to draw my conclusions. So I hope this has given you an interesting overview of some of the technologies that we're developing at the moment and the future direction of travel, where this technology can go. As I said, I think these systems will be deployed firstly on existing agricultural vehicles, but then I think on a longer term we can hope to see smaller robotic systems that will do some of these tasks. And hopefully we can get from the general purpose tractor to the general purpose robot on the farm that can do lots of jobs on the farm. So for me, as a researcher in computer science and autonomous systems, I think they're an excellent enabling technology for precision agriculture. I think it's important to note, however, that robots and humans are good at different things. So I don't think it's a case of robots replacing humans. It's a case of robots helping humans to become more productive and hopefully providing more interesting work for them as well. So I think we'll go from agricultural machines to robot co-workers. So it might be that the farmer of the future is something like a shepherd with a flock of robots. I think, however, we're not going to see full autonomy just yet. I think it's very important, actually, that we have a human in the loop, especially if we need someone to train the system or to supervise and look after the system. So, for example, the person that's driving the tractor on the farm might also be the one that's training it to recognize broccoli or whatever the job may be. And I think it's essential that all of these systems are able to self-improve. They're able to learn from their experience. And that's really key, I think, and that's the glue, if you like, that holds all this stuff together. I think that's a really core thing that we as computer scientists need to develop for the agricultural robotics systems to work. So that's just about it. I just want to acknowledge the people that have done this research and the people we've worked with. And then finally, just to say, if we're currently looking for people for projects, we're looking for new lecturers, new postdoctoral researchers, new PhD students. So if you know anyone that might be interested, please send them our way. That's about it from me. So thank you very much.
Thanks very much, Professor Duckett. Before I introduce our second speaker, I just want to remind you of the Slido app. So if what you've heard so far is prompting some questions, please do go to Slido, www.sli.do, and put in your questions. If you're in the audience here in particular, please do say who you are and indicate the fact you're here in the audience, and I'll get you to ask your question at the end when we have the Q&A. I also mentioned that we're doing polls on Slido, and James put a poll up on the screen, but I didn't actually introduce it. So here's the poll. I can see quite a few of you who have already voted. So the first poll question was, how would you rate the current importance of automated technology and associated software as part of your business? So today, how important